Okay, so these are Chapter 5 discussion questions, starting with West number 1. It says, if two forces act on a body, could the body possibly move A at a constant speed or B at a constant velocity? Sure. Can you give me an example?
Well, if like the forces, like, no, I don't. I'm just gonna explain.
Okay.
They have to have two equal forces.
Exactly. They'd have to be equal forces, because that's our equilibrium's our only case where we would have constant speed or constant velocity. All right, next part. Could the body's velocity be 0 only for an instant, or d continuously with two forces?
When it says for an instant, that means it's changing?
Yeah, that means it's going to be accelerating. So can you have two forces on a body and it accelerate? Sure. What would have to be true, though? One would have to be bigger. Okay, and what about at rest continuously? It's just not moving. Sure, they just have to be equal. Okay. All right, Erica, number 2. All right, you got these little vector diagrams here. It shows 4 forces of equal magnitude. Do any of the 3 of them look as if they will leave a body's velocity unchanged when all 3 act on the body? If so, which 3?
A and B automatically cancel each other out.
Okay, if it said which 2, A and B would be a good choice.
Yeah.
But which 3?
I don't know.
Think about our force table lab. When that little ring in the center wasn't moving in the force table lab, all the vectors added up, all the force vectors added up would equal what? 0. So which of those 3 vectors could you add head to tail and get back to where you started from?
A, B, and D, I guess?
No, because A or B are going to cancel, and that's just going to leave you a D.
Okay, so... Oh, A, C, and D. If you move them.
Except not A.
So I think that has to be D.
Yeah, because just try to picture squeezing them all in there. You know, head to tail, you know, B plus D plus C gets you back to the beginning of B. Gets you to the tail of B. Does that make sense?
Yeah.
B plus D plus C would cancel out. That would be an equilibrium. The net of those 3 is 0. All right, number 3. No Thomas. Daniel. All right, you've got an overhead view of 4 situations in which forces act on a block that lies on a frictionless floor. If the force magnitudes are chosen properly, in which situations is it possible that the block is A, stationary, and B, moving with a constant velocity? Which, as far as the forces go, is there any difference really to us in stationary or moving with a constant velocity? No, that means the same thing. That means forces are balanced. So it says the magnitudes of those arrows, if they're chosen properly. So we can adjust the magnitude as needed, but there's only, how many cases? 2 cases where they actually could cancel out. So what do you think? Exactly, very good. 2 and 4. 2 is just a left and a right. That could cancel out if you 5 and 5, 6 and 6, if you chose the magnitudes properly. And 4 could cancel out as well. F1 does not look like it has a very big component to the left, but if we set it at whatever we want, we would have a left component to balance out F2, F3 is down, but we have an upward component to balance that out. So it would only work out for 2 and 4 that we could be in equilibrium. All right, number 4. Tyler. It says a vertical force F is applied to a block of mass M that lies on the floor. so either up or down. What happens to the magnitude of the normal force on the block from the floor as magnitude F is increased from 0 if F is downward or B upward? So you've got a block on a floor, you're either pushing down or pushing up, maybe with a rope somehow. If you are pushing downwards, what happens to the normal force? It has to get greater. If it doesn't get bigger, then we're crashing through the table. So we'd have to push back more, because it's like the weight got heavier, except it wasn't the weight, it was an external force. All right, what if we were lifting up on that block? What would happen to the normal force? It would be less. We wouldn't need as much upward force because we have the help of the force we're applying. All right, number 6. Zach. All right, this picture, in the picture, does the vertical component of force F help support the box, or does it press the box against the floor? Yeah, it's certainly not pushing against the floor, so it's supporting it. Then part B, suppose the mass of the box is m, then is the magnitude of the normal force on the box equal to, greater than, or less than mg? So it's sort of the same question as Tyler's question. You have this external force, so is the normal force truly equal to the weight here? No, because you have this extra force. But does that extra force increase or decrease the normal force? Decrease. It's sort of helping lift it. So we don't need as much normal force. And then just a trig question there. Is the vertical component F times sine of theta or F times cosine?
Vertical component is
Yep. Sine. Okay. Next one, we're skipping 7, number 8, elevator problem. All right, Brandon. All right, an elevator is supported by a single cable and there is no counterweight. The elevator receives passengers on the ground floor and takes them to the top floor where they disembark. New SRO walking by. All right, new passengers enter and are taken down to the ground floor. During this round trip, A, when is the tension in the cable equal to the weight of the elevator and the passengers? When is the tension in the cable equal to the weight?
when they're moving upward
At a
what?
or downward at a,
Constant.
yes, at a constant velocity, or when they're at rest, because that would be constant velocity too. Okay, when would the tension in the cable be greater than the weight?
Accelerating upward.
If you're accelerating upward, or what's the opposite of that? Not accelerating downward.
Okay, slowing down. Going downward? I don't know.
Yes, as it's going down, but slowing down, because then we would be slowing down by a greater force up. Okay, and then the last part, when is the tension less than the weight?
I guess if it's going up but slowing down and then speeding up going downward.
Yes, going up, but slowing down, or going down, speeding up. Very good. All right, Emily, number 9. Because this is just a common scenario here. In the picture below, a massless rope is strung over a frictionless pulley. A monkey holds onto the rope, and a mirror having the same weight as the monkey is attached to the other side of the rope at the monkey's level, as you would have. Can the monkey get away from the image, either by climbing up, climbing down, or releasing the rope?
Climbing up
it would still have it, because it would pull it up.
Exactly.
Pull the mirror up, climbing down. Well, it depends on how you like climb down a rope.
If he's,
Down,
mhm.
is he pulling on the rope? Like making it?
There would still be tension in the rope, but as he goes down, like, does the rope just stay there?
Yeah. Well, does the rope move when you go down? But you're not pulled. I didn't think it.
It's not like nailed to the ceiling. It's just going over this pulley. So,
The rope would go down.
yeah, the rope.
Go up. I don't understand how the mirror, if it's the same thing.
The mirror is attached to the rope. So if the rope's going down, the mirror is going down. In order to climb down, it's like the monkey's like
Oh, yeah, okay. Okay.
pushing the rope up,
So then
Yeah.
the mirror goes down.
the mirror goes down.
By releasing the rope, he would get away.
Okay, well, if he releases the rope, he's falling at free fall. What about the mirror? So he cannot. So no matter what he does, I mean, he can pull up and he'll go up, and the rope or the mirror will go up, or he can go down, but the ropes and the mirror's going to go down, or he can drop it, but there's no escaping the mirror. All right, so Connor, number 11, it says a block is attached to a rope, or sorry, by a rope to a bar that is itself rigidly attached to the ramp. Tell whether the magnitudes of the following increase, decrease, or remain the same as the angle of the ramp is increased from 0. So I'm simply making the angle bigger. A, the block's weight component along the ramp. It would increase. If you are increasing the angle, the side opposite that angle would have to get bigger. Does that mean the weight gets bigger?
No.
No, just that component. Okay. How about B, the tension in the cord?
It would increase.
It would increase as well. And I didn't finish drawing my picture, but if weight parallel is increasing and the block is still not moving, the tension going the other way would have to increase to match it. How about C, the block's weight component perpendicular to the ramp? Good, it would decrease. If one's going up, the other has to go down to keep our triangle all the same. And then D, the normal force on the block.
It should stay the same. No. It would decrease.
It would decrease as well, because it would have to match weight perpendicular. And if that went down, then it would go down. All right, very good. All right, 4 more. Getting there. All right, Wes, number 12. Similar thing. Says a box of donuts has a weight component of 5 newtons along a frictionless ramp. Why we're pulling a box of donuts, I don't know. I would think that would be light enough that you could pick it up. Did I draw that right? A weight component of 5 newtons along a frictionless ramp. Okay. The force of the box, force on the box from the cord has a magnitude of T. So again, very similar to Connor's question. That should be about it. The force on the box from the cord has magnitude T. When the box is either stationary, B, moving up the ramp at a constant speed, or C, moving down the ramp at a constant speed, or D, moving up the ramp at decreasing speed, and E, moving down the ramp at decreasing speed. Okay, in all these scenarios, I want to know, is T equal to, greater than, or less than 5?
Stationary is going to be the same.
Good?
Moving up the ramp at a constant speed. Should be the same.
Good?
Moving down should be the same.
Okay, so stationary and constant speed, they're the same. All right, now you've got your, what was D? Moving up the ramp at decreasing speed. Very good, it's got to be less because it's slowing down. Next, down the ramp at decreasing speed. It should be more. Good. And again, given enough time, You know, if this is like 10 newtons and it's moving down the ramp at decreasing speed, given enough time, it would stop in reverse directions. All right, 13. Erica. This is sort of like the penguin problem, but it says you have 4 blocks being pulled across a frictionless floor by force F. What total mass is accelerated to the right by a force F? What total mass is being accelerated by force F?
The mass of all of them.
Yeah, the mass of all of them, 20 kilograms. How about by chord 3?
Wouldn't that just be the 18?
Good, that would just be the 18, chord 1, the 10, and then it says rank the blocks according to their accelerations, greatest first. Are they staying together is the first good question. Or are they ripping apart? Are they staying together? They're all tied together. We would assume they're staying together. So, is this one accelerating faster than this one because it's front, or vice versa? Or are they the same?
Should all be the same because
Yeah, they should all have the same accelerations because they're staying together. It's not like one is speeding up faster than the other one. They're all stuck together. So we've talked about these before. You could draw your free body diagram, you know, a couple different ways. You could draw it as all one big thing with this being the force acting on it, or you can draw them sort of individually or maybe in little groups. If you just draw this one box, though, you've got to be aware of the tension force acting on it the other way if you're using that. Or you can do them all together and say the mass total will be 18, and we would just have that force, whichever. So they all have the same acceleration, and if they all have the same acceleration and they're all different masses, then they can't all have the same forces. They must all also have different forces. So which force would have to be the greatest? The force from force F, the one in chord 3, chord 2, or chord 1? I guess it's asking about the chords, but
Oh, no, it's not like force F.
force F, and then
And then it have to be 3.
good, 3, 2, and 1. So this would have to be the next biggest force because it's kind of pulling all of this mass. This would be the next biggest force, and so on. Okay, similar to that question, Daniel, we have another question where we're just pushing on blocks, blocks into blocks. Almost done. 14 and 15. Okay, so we have 3 blocks being pushed across a frictionless floor by horizontal force F, over here. What total mass is accelerated to the right by force F? Just look at the picture. What's the total mass that that force is pushing on?
17.
Good, all of it, 17. How about force? It says 2, 1, so like the contact force between 2 and 1. Yeah, it would just be 7, and then the next one. Wait, not 7. The force here pushing to the right is only affecting these 2 blocks. So not 7, but 12. All right, and the next one? The force of the contact force between 2 and 3? Just 10. Rank the blocks according to their accelerations. Is one accelerating faster than the other? We would not think so. They would all be staying the same. They're all being pushed into each other. So all the same. but rank the forces according to their magnitude. Which would have to be the greatest force there? The original force, F1 or F2?
F1.
Well, F1 was only pushing 12 newton or 12 kilograms. Which one's pushing the most mass? Just F. Okay, so F is the most, then that one. That's it. All right, and last but not least, number 15, Tyler. Okay, the picture to the right shows 4 choices for the direction of a force of magnitude F to be applied to a block on an inclined plane. The directions are either horizontal or vertical. And for choices A and B, it's not a strong enough force to actually lift it off the plane. So rank the choices according to the magnitude of the normal force on the block from the plane, greatest first. So that's kind of like the question you had already, except now it's on an incline. Which 2 forces, Tyler, would cause the normal force to be a greater force? Well, C and D. So the normal force is coming out from our surface. So if I'm providing force C or D, pushing sort of into the surface, I'd have to have a bigger normal force. But which one would be bigger based on the picture, C or D? Which one would cause a bigger normal force? Yeah, I would agree D. And you just have to kind of think about which component this way, perpendicular. So along this line, which would be the line for the normal force, the component of D would be bigger than C. So D, then C, then what do you think? A, then B.